Do you know the answer right here for 1? So in here we have some functions, or you may say some maps from R2 to R2. The question is, which ones are linear transformations? A short answer to this question is that if you see a map given by this one, this formula, you have a linear transformation. In fact, a linear transformation from R2 to R2 must be given by this formula. A linear transformation from R2 to R2 must be given by the following formula. Therefore, the answer we have, if you knew this, the answer is the last one, this one, yeah. Do you know why we had this? For example, the first two, they are not linear transformations. And the last three, they are linear transformation. Because if we accept this one, we use this one, we say that, for example, the last one, if you consider the constant transformation, which transform any sy into the point 0, 0, this is also a linear transformation, because if you apply A, B, C, D, which are 0, then you get this one, right? Why do you have this formula? Yeah, this is very simple. Yeah. So if you want to know why we had this, then let me show you very quickly. A linear transformation from R2 to R2 must be given by this formula because of the definition of a linear transformation. If you write TSY as TS10 plus Y01, so according to the definition of a linear transformation, you can write this as this one. And now from here you get the answer. So let's say T10 is AB, and this is CD, let's say. Then from here you get AS, maybe I write C right here or something. Let's say this is C, and this is B. So you get AS plus BY, CS plus BY, right? Yeah. Anyway, so question 1 is that it should be given by this formula. A, B, C, D, right, are real numbers because of the definition only. All right, so let me go to the second question. Is that all right with the first one? Do you have any question? So go to the second question. Now, in here we have T, the vertical shear from R2, in R2 with the factor K equal 9. The definition of a shear you can see in the note right here. Open this one for the definition. Yeah, it's just a one-page note. Right here, we had two different types of shear. We can have a horizontal shear or a vertical shear, and the definition are given by these two formulas. So basically, let me give you the definition. Maybe I focus on the question, so go for this one. Is that all right with question number one? If you don't have any questions, so let's go to the second question. What's a vertical shear? This is the idea we have. You can see in the note. So let's say you have a point SY right here. So you know this is S and this is Y. If you consider a vertical shear, you go up. So let's say T of SY now is this is SY, right? But you go up with a factor of Y. So this is T of SY. So you still have the same S, yeah, for T of SY because you go up in the vertical direction. So that's why we say vertical, we go up. So T of SY, we still have the same S. Yeah, the S component is the same, you see. But for the Y component, we add a factor of the S component. So we have Y plus KS. Therefore, the answer for A right here is all right here. So the last one, right? We had the same S because we go up, right? We go in the vertical direction. And the Y component, we add the factor K, S, yeah, K is 9S. So we add a factor of S, we say 9S into the Y component. So the answer, by definition, is SY plus 9S. So when K is 9, you have this one. So this is just by definition. Yeah, you open the note, you see the definition. Now let's do the second part of question. Find the standard transformation of this one. What's the standard transformation? It's just the transformation with respect to the standard basis, right? So let me write. Standard transformation of T is just the matrix of T from S to S. S is the standard basis. R2 so yeah, so this is the definition of the standard transformation of T definition. So in order to find the standard transformation, according to this definition, you need to find the image of T over the standard basis. So we have T SY SY plus 9S. So T10 is 1, 9. T01 is 0, 1. Right here, we consider 1, 0, 0, 1 because we are considering the standard basis for our two rate. You know that. So you have, so from here you get T from S to S. This is from the last class, right? So I think you remember this one. You put 1 right here and 0, 1 right here. So this is the answer. So the answer to the question we had is the second, right? Now let's go to the third question. Is that right? It's a simple question. Do you remember that the definition of the transformation matrix of a linear transformation? We got it from the last class. So let's do the third question. Is that right with the second question? Now, let's go to the third question. Question 3. We want to, T right here is a linear transformation. UV are two independent vectors in R2. So you can consider the set of UV as a basis for R2, right? And we want to find the corners of this T of T of T. This is the composition of 3 times of T, right? In order to do this, you only need to find what we have for this as a linear combination of U and V, right? And then we get the answer. So let's do this. First, we do T 7U minus AV. We get this one as, yeah, so you can write this, right? Because of the definition of a linear transformation. You see, from the definition, right, you can write this. Now, so this is the first one. So let's do one more time. So you have T of T. Now it's equal to T of 70U ATV, right? And then you get 7T of T U minus 8T TV. Yeah. And now you get one last time when you have T of T of T, right? So this is just T of so now you can write T 7T T U 8 T TV. And then you get 7 T T T 8 T T TV. Yeah, so many parentheses. Anyway, so what you can write right here in summary is just the following one. In the end, you may say that this one is exactly 7 TQ. Maybe if you want, you can write like this. It's better. Minus 8 T. Yeah, anyway, so that's exactly what we have. All right, so, but I think let's continue with this one. I just put a summary for what you say, but this is not necessary. So let's erase this one and continue. So, you know, TU is AU, right? TV is 5V. So you see it, you see this in the question, right? TU is AU, TV is 5V. Therefore, you can get this one and this one. So I think you can say this one now is just right. And then you get 8. So you get 8 T AU, right? And then A squared TU, and then you get 8 AU. So in the end, you get AQU. So anyway, if you see this, if you look at this one, you just say, all right, T of TU is just AQU, right? Right here, I just get it slowly. Anyway, so the one right here would be 5QV, right? So in the end, the answer to the question would be, now you can write T, 7U minus V is just AQ, V minus 5Q, sorry, U minus 5QV. So the answer is, you want to find the corners. In the basis UV, of course, the answer now is AQ minus 5 cubed, right? Yeah, so that's question number 3, very quickly. We just used the definition we have for a linear transformation. Sorry, I forgot 7 right here. All right, I forgot 7. We have 7 right here. And then we have 8 right here. You see, they are right here, 7 and 8. So in the end, the final answer would be, so let me rewrite the answer. So 7, 8 cubed, 8, 5 cubed. Yeah. Now let's go to question 4. I think you can do question 3, right? So just apply the property we had in the definition. So let's let's go to question number 4. Is that right? Now, let's go to question number 4. What do we have in here? So in here we have T1 as a linear transformation. It's defined by the reflection in the line y minus 4s equals 0. Let's find the formula of T1. So let's do it. Is that all right with question number 3? Let me go to 4. So T1 is, by definition, you have the line y minus 4s equals 0, something like this. T1 is the reflection in this line. It means if you consider sy right here, then this one is exactly T1 of sy. Yeah, by definition, right? So you know exactly what we have for T1, and the question is to find the formula of T1. So how to find the formula of T1? You only need to find the standard matrix of T1. And in order to do that, you only need to find the image of T1 over a basis. So that let me write that. So to find T1, let's find the image of T1 over a basis. You only need to find a basis of R2 and then find the image of T1 over that basis. It's all right. So let me, this is 0. So let me make this bigger. All right, so first, now let's consider T 1, 4. One 4 is a point on the line. Is that right? 1, 4 is right here. Do you see that? Because when you consider 1, 4, you see we have it on the line y minus 4s. Therefore, T of 1, 4, sorry, this is T1 is the same as 1, 4. Is that right? So we get, remember that what we are doing right here is to find the image of T1 over a basis. So 1, 4 is the first vector we have in the basis. T1 of 1, 4 is the same as 1, 4 because 1, 4 is on the line. The reflection of 1, 4 is still as 1, 4, right? Let's find another vector for the basis. So let's consider how to find another vector for the basis. You may consider this line. Do you know an equation for this one? To find an equation of this, you may look at this, find a normal vector for this one. So it's minus 4, 1, right? Therefore, if you want to, the line right here is perpendicular to this one. Therefore, this one you may consider this. Let's say this is n1. The one right here would be 1, 4, right? So the equation right here is s plus 4y equals 0. Is that right? The line right here we say perpendicular to this is s plus 4y equals 0. You can find this one, right? This is just from high school geometry. In order to find this, you look at a normal vector we have for the line. We have at first we have minus 4, 1. So the one right here would be perpendicular to this, so you have 1, 4, right? Yeah. Now, is that right? Any question? So what I'm doing is I try to find an image of a basis over T1. This is the first vector we had in the basis, and I already got the image. I need one more. So I can consider this line, we say perpendicular to the 1 minus 4s. And now I may consider this one, let's say 4 minus 1 is, of course, on the line right here, because when I consider 4 for s minus 1 for y, I get 0. So I may consider 4 minus 1 right here. We'll see the image of this one. Of course, you may guess it's right here, so it would be minus 4, 1, right? So this one is the reflection of 4 minus 1, right? Because of the definition of T1. Yeah, it's all right. So so if let's say 4, this one would be T1, right? So it would be minus 4, sorry, yeah, 1. You see it here. Anyway, so yeah, that's enough. It's time to get the answer. So now you can consider T1 from S to S. By the way, S is the standard basis. You only need to find this in order to find the formula for T1. Let's say E right here is the basis that we have right here. So let's say E, the one right here, 1, 4, and 4 minus 1. I put the name E for the basis that we have got right here. So I can go from S to E, and then from E to S. Is that right? So from S to E, you know, this one is just and this is just 1, 4, and the guy right here from E to S, because you already got the image of T1 over E, so you know the answer for this is yeah. Is that right? Any question right here? So let me say again, I'm trying to find T1 from S to S because if we had this, we get the answer. I use the formula we got last time. We go from S to E using P. P is the transition matrix. And then I need to go from S, E to S, right? So then you get from S to S. P from S to E is defined by this, this is from, what we have in the definition, right? And T1 from E to S is this one because you already got the image of T1 over E, right? Now, so from here you get the answer. So let's see what we get right here. I need a calculator right here to get the answer. So we need to take the inverse of this one. So the one right here, we have 1, 4. And this one is 4 minus 1. So this is what I get. All right. And now it's time to get the answer. So the answer now is, we had this. Right? And you get the formula. Yeah, so that's the answer we have. Any question? Do you have anything that you don't understand right here? So the idea right here is that we find an image of a basis. That's enough to get the whole formula. If you want to find the formula of T1, the only thing you need is to find the image of T1 over a basis. Any basis you have. Right here, I consider 1, 4, and 4 minus 1 just because I can get the image easily, right? 1, 4 is already on the line, of course, the image is also 1, 4, right, by definition of T1. And the second vector I need right here is 4 minus 1. 4 minus 1 is right here, then the image is minus 4, 1. It's right here, right? 4 minus 1 is here, and minus 4, 1 is here. Anyway, so I get a basis 4, 1, and 4 minus 1. I put that as the name E, right? Now it's only about to get the basis, the, the matrix of T1 in the standard basis. S, so T1 from S to S is, you know this, right? Yeah, we had this formula. We can go from S to E using P, and then from E to S. Yeah, so that's the first part of the question. Now let's see what we have in the second part of the question. Any question? Right here we have T2, the clockwise rotation. You know, you can use this formula for that. And T3, the projection on the line, and we want to find the matrix of the composition. In order to do this, you only need to find the matrix of T1, T2, and T3 in the standard basis, and then you consider the product. So let me do the second question. First, I need to find T2 and then T3. T1 is, you know, is already here, right? We got T1 already, so we only need to find T2 and T3. Now let's see. So let's find T2 from S to S, and also T3 from S to S. And then the answer would be T1, T2, T3. Now let's find T1, T2. T2 is the clockwise rotation, 90 degrees. If you use the counterclockwise, you use this formula. If you use clockwise, you put minus into the angle, right? So the answer for this is cosine minus 90 degrees. Right here we have minus because right here we use the clockwise, right? Clockwise we have minus. Counterclockwise we don't have minus. Right here we have 90 degrees, 90, so I put 90 right here with minus sine, minus 90. Remember that we are using degrees in this formula, not radians. So what you get is 0, right? What do we have right here? We have 1. So T2 is done, right? So let's go to T3. For T3, you do the same thing as you saw in T1, right? Basically, you find the image of T3 over a basis. Do something similar as T1. So let me do that. Let's see what we have for T3. Is it the projection onto the line for y plus s equals 0? So you may consider it right here. this is the projection. It means that if you consider sy right here, then this one is T3 of sy, because T3 of sy is the projection of sy on the line 4y plus s equals 0. So this is the definition, right? Again, now in order to find the matrix T3 from S to S, we need to consider bases. The first one I see is that I may consider this one minus 4, 1 because it's right on the line, right? If you consider T3 of minus 4, 1, you get exactly minus 4, 1 because the projection is still the same point, right? Yeah, the projection right here is exactly the same point, right? Now we need one more, so again, we may look at this one. What's the equation of this? Y minus 4s equals 0. Is that right? So this one you have 1, 4, right? And this one you have minus 4, 1. Yes, yeah, that's right. Again, we need, we can look at one point in here. So let's say we consider this one. I think this one is 4, 1, right? 1, 4. You see 1, 4. What's the projection we have on the line right here? It's exactly the origin, right? This one is T3, 1, 4. Because we consider the projection on the line right here, right? So you get 0, 0 for this. Yeah, and that's it. Now you have E, the basis, and it's time to do the same thing, right? Is it right? You see the projection of this one on the line right here is the origin by definition. All right, so let's do the same thing as we did for T1. I'm going to find T3 from S to S. I may go from S to E, and then E to S, right? If you go from S to E and then E to S, you go from S to S. And by the way, when you do this, you need to put the matrix T on the left. So this guy is from E to S inverse, right? Because it's similar in this way. E to S, you have this one. Yeah, you see E and you write from E to S. Yeah, you had this. And this one, you know, yeah, you get this from the image of T3. All right, so in the end, you get T3, right? You already got T1 from the first part of the question. You already got T2 from the rotation. And now you consider the product T1, T2, T3, you get the answer. So I think you can do that. So in the in the end, you get the answer. Yeah, so matrix right here. All right, so maybe I stop here. Yeah, so just say that, you know, you only need to consider this one. because the matrix for the composition is just the product um, of the corresponding matrices for each transformation. T1 is just one. Let's say T1. Let's say T2. And let's say T3. So you get the answer right here. All right, so that's question 3. Do you have any questions? So let me go to question 5. All right, so I think question 5 is similar to question 4. Now let's do this. Is that right with question 4? So the idea is that you only need to find the image of a pixels. That's good enough to get the whole transformation. So let's do question number 5. Again, right here you see F is the rotation, 60 degrees counterclockwise. We can easily find a matrix for this from the formula, right? G is defined by this one, so it's explicit, right? Phi M, so that the composition F of G is the reflection in the y-axis. So first, you know, you want this. This is what you want. So it means that, let's say they say T or something, then it means that F G would be T, right? So all you need to do now is to look at this equation and get the answer. Yeah. So first, let's find the matrix right here. First, T right here is the reflection in the y-axis. That's the name I put for the right-hand side. This is not a Newton rate. You just find an image of T over a basis, and you get the answer. So let's do this. Let's do this one. Now, first, what do we have for T? The y-axis is the one right here. You see, right? This is the y-axis. It means if you consider 1, 0, then t of 1, 0 is minus 1, 0, right? Yeah, so we get the first image of the first vector. We may need one more. 1, 0 and 0, 1, that's all right for a basis, right? 0, 1 is right here. And of course, you get the same 0, 1. Right? Because the reflection of 0, 1 with respect to the y-axis is still 0, 1, right? And now you get, you do the same thing, right? Do the same thing. You may say this is the basis E, but in fact, E is just the standard basis. You don't need to do anything. So T from S to S is just 1. Right? Now you get the right hand side, right? So look at what we have for the left hand side first. Go for this. What do we have from F? F from S to S. It's the rotation counterclockwise 160 degrees. You already got the formula, right? So cosine of 60 minus sine of 60, sine of 60, cosine of 60 right here. Right? You got it from this one, right? Counterclockwise 60 degrees. So you get this. And then you have yeah. Now do the last one, Chi, right? From S to S, what do we have for this? You only need to use the formula right here. Q 0, 1, 1, 0 is, minus 1/2 m, right? Q of 0, 1 is m 1/2. So from here you get G from S to S is just this one. All right, so now the question now is just, so now you focus on these three matrices. The first one is right here, then this guy, and then this guy. So now you only need to find m so that right, you get there. Get there. You only need to multiply them together on the left and solve some equation. I think so. Yeah. So yeah, do this and you get M. So let me go to the second part of question. Yeah. So yeah. So for my question, in the end, I get the answer root of 3/2. All right. So I solve this and I get that. All right. So now I need to use this one for the second part of question. For the image of this through G of F. This is very simple because, you know, if you want to get the image, it's all right here. All right, so let's go to the second part of question. Get the image. Image of G of F of this one. So you get maybe like this, so that you get. Now you only need to do this. You get the answer, right? When you consider G in the standard phases, F in the standard phases, you consider G S to S times F S to S, you get the phases of G of F in the standard phases. And you multiply that by the input, -1, -8, you get the output for the image. Remember that now you don't have M, it's just 3/2, right? You put that into. All right, so let's go to the third part of question. Find the dimension of the kernel of this G of F of G of F. So let's say, remember that now M is root of 3/2. For this one, we can use the following formula. You know, the dimension of, so let's say if dimension of the kernel of T plus the dimension of the image of T is the dimension of the domain. What's the kernel of T? Let me remind you the definition. Kernel of T is the set of S in the domain so that T of S equals 0. What's the image? The image of T is the set of TS for S in the domain. Yeah, so you get the definitions for the kernel and the image. All right, so let's apply this one. Let's apply this one to the question. By the way, let me, maybe I said this specific fact. Number one, fact number two, if you want to find the dimension of the image, you only need to find the rank of T in the standard phases. So the dimension of the image of a linear transformation, for any linear transformation T, It's exactly the same as the rank of the matrix of T in the standard basis. S is the standard basis. Yeah. Now, um, so let's do 3. All right. So what we have for this now, you can see the question is about to find this one. Sorry, this is this one. This. If you consider this one, you get the dimension of the domain, right? So right here, we use the formula right here. The domain right here is, R2, right? This is the domain you have, R2. So you get the number 2 for the dimension. If you consider this one, if you set T for this, then this one goes from R2 to R2, right? So this is the domain you have. And the dimension is, of course, the number 2. So the question is about this one, find this, right? In order to find this, you may look at this one, find the dimension of the image. The dimension of the image is the rank of this. Yeah. The dimension of the image is just the rank of the matrix of T in the standard basis. And it's the one right here. You can get this one right. Use a calculator. Because you already got GF, right? You got the 2 matrices. M is just √3/2, right? You use a calculator, you get this one. And then you get the answer. So you get the answer. Is that right? You can find this GF, you can find this matrix, right? Because you already got G and F, you see them right here, right? You see what we get for G, and this is what we get for F. M now is just √3/2. Yeah, it's a subspecific number. Now let me do the last question and then we end the class. The last one, I say that the last one is also from this, you find M so that the dimension of the image is as small as possible. The dimension of the image is equal to the rank of the matrix. So for this question, you only need to find M so that the rank of the matrix is minimized, right? So let me do that question also. Now, question number 6. The dimension of the image is always the same as the rank of the matrix in the standard phases. What do we have for this one? You get it from the question. T of E1 is 1, 1, right? T of E2 is minus M, M minus S. T of E3 is minus 1, 2 minus M, and the last one, minus M, minus M. Therefore, you get the answer for the matrix 1, 1, minus M, M minus S, minus 2, 2 minus M, minus M, minus M. So the question now is, so what's M so that rank of this is minimized, right? Yeah, that's the answer. This is very simple because you have only 2 rows, right? If the 2 rows are not proportional, you get rank equal to, and that's the mass, right? You don't want the mass, you want the mean. It means the 2 rows would be proportional, right? And the only way we have that is when they are the same, right? Because right here you have 1 and right here you have 1. They are proportional only when they are the same. So the answer would be 3, right? Yeah, so that's the last question.